Thanks, though. Yeah, so we have to use that analogy that we were looking at last time that relates the strength of an acid to its conjugate base. So let me see. Remember that relationship was something like this, that Ka times Kb equals Kw. So we see that something that we sort of hinted towards all along in this chapter, and that was that they were inversely proportional. So, for example, Ka equals Kw over Kb, or vice versa. So I can rank the acids that they gave me, and they gave me 3 acids, and I see the one that's the largest is HF. So strongest acids in that list would look like HF is greater than HNO3 or 2, and that's greater than HCN. So right off the bat, that must mean that the conjugate base Cn minus has to be greater than the conjugate base NO2 minus, which is greater than F minus. And now they threw in a Cl minus in there, and that was part of your question. So what is Cl minus? Chloride. And how does that fit in? And what kind of a base would that be? And we're just kind of nipping at the heels of this concept about conjugates and their relative strengths to the acids. Now, Cl minus, you can consider that a conjugate base. What is it the conjugate base of? Anybody out there?
HCl.
Yeah, HCl. And HCl is, what is that?
Hydrochloric acid.
What kind of an acid?
A strong acid.
Strong acid.
Yeah, righto, you guys. So this equilibrium, there's a tiny little arrow that goes back. It's so small you can't see it. It's microscopic. This reaction lies to the right. It's a strong acid. That makes this guy, this conjugate base, so weak that we sometimes call those kind of ions spectators. So that's going to be the weakest base of all that, of that list. So right off the bat, I see it's in the first choice or the second to the last. Looks good. And then we got water in there. So water's amphoteric. It could act as either an acid or a base. So where do you think water is going to go in this list?
At the start.
You think it's a stronger base than Cn minus? For example, if I have water, you know the pH is 7. If I put Cn minus in water, do you think the pH is going to be greater than, less than, or equal to 7?
Less than?
Well, less than would make it an acid. If it's less
so
than 7. right? That's the reaction that's going to happen when you put a base in water. A base, according to Bronsted definition, accepts a proton. So it's going to form some of that weak acid. And in the process of coming to equilibrium, it's going to form some hydroxide. That hydroxide is going to add to the hydroxide that's already in water, which is 10 to the minus 7. That's all that water is going to give you. So Cn minus should give you more. In fact, all of these guys are going to give you more. So I think now you know where water goes on that list. What do you think? Do you understand why it goes at the end after F minus?
Yeah, should be the weakest.
Yeah, it's the weakest base of that list. So it's going to go after F minus. So we just say, okay, after F minus, then comes water, which is good pH is 7. And then the weakest of all of those bases would be Cl minus, the spectator. All righty. Any questions on number 5?
No, that was it. Thank you.
Okay, cool. I shouldn't have gave you the answers, but oh well. Right, that's due tonight. So you got a free one. All right, let's take a look at number 9. This one I've been putting off for a while to give you a chance to look at it to see what's going on. All right, for number 9, it gives you these equilibrium and then it asks you to identify the strongest base. Now, it tells you one thing about these equilibrium and that they lie far to the right. We looked at our choices and we said, well, CH3 O minus, that could be a base. Then there's an alcohol, which shouldn't be a base at all. If anything, it's going to be a really weak acid. And then we got Cn minus, that could be a base. And then H2O, which is either 1, and NO3 minus. Does anybody recognize what that is? Could it be, first of all, for NO3 minus, could it be an acid or a base? What do you think?
A base?
Yeah. Why do you think, from what we talked about last time in our discussion, why do you think NO3 minus might be a base?
Because it has a negative charge on it?
Yeah. Okay, cool. So we go ahead and react it and we say, okay, Bronsted base, it's got to accept a proton. And so if we do that, we write our equilibrium and say, oh, look, yeah, maybe it is a base. But you have to say, well, wait a second, hold the phone. What is this? It's a strong acid. And you don't form strong acids. Those guys break up in water. They don't form. So even though nitrate can be considered a base, it's the conjugate base of the strong acid, just like Cl minus. So it's a spectator. It's just going to float around in water, not going to bind up with anything. All right, so I guess then our only choices, and I think we said this before, are which ones? For the strongest base competition.
Would it be CN minus and CH3O?
Yeah,
Right?
correct again. So what in those equilibriums above can give us some clues as to the relative strength of those two? So let's take a look at the equilibrium that they give us. We have nitric acid, which is a strong acid, plus cyanide, which is a weak base. So we got a strong acid, a weak base, and it says it lies way to the right. And that kind of makes sense because it's an acid-base neutralization, and there's a strong driving force for that, as we'll see in our discussion today. Now, does that tell us anything about the relative strengths of Cn minus and CH3O minus? I'm not sure it says too much. It could be just a distraction. So let's go to the next one. I have HCN plus OH minus, and that makes water and CN minus. That lies way to the right. Now, if you think about this for a while, and that's why I wanted to give you a few days, then you might say, okay, that's true. And I've thought about it, I slept on it, I still don't know what's going on. But if that reaction lies way to the right, then where does this reaction lie? Anybody?
The left.
Yeah, to the left, because, and you know that because you know something about how equilibrium behaves. So if I had an equilibrium constant for that second reaction, then the equilibrium constant for this reaction is going to be 1 over that for the second. And if this guy is very big, which indicates that it lies to the right, then this guy is going to be very small and it lies to the left. All right. Okay, so now that's given us some information we might be able to use here. Now the next reaction, what does it say? Where does this one lie? Anybody?
To the right.
Yeah. Okay, now can you rank the relative strengths of this guy versus this guy given what we just analyzed? Which one's stronger?
The CH3O minus.
Yeah, why do you think?
Because it easily it doesn't easily dissociate.
Well,
So
I think what you wanted to say was
I
it
mean the
easily,
acid
more
doesn't
easily
easily.
accepts a proton. That's what
Yeah.
bases do. Yeah, and you're right. That's exactly right. And so that's the way to logically, I think, see through this problem and pick at the right answer. The other guys, the other choices, we got a spectator, we got water, which is neutral, and we got an alcohol that, if anything, is a very weak acid. Most of the time, we don't even consider alcohols as acid because that bond here is still fairly strong. All righty. Any other questions on that or any other ones in this homework set? All right, nothing. Okay, so let's go to our discussion from last time. First of all, before we get into this, are there any questions on any of the stuff that we talked about before, like salts and, you know, you're going to have problems now that require you to remember Chem 200 solubility rules, and be able to identify what's in the water, and furthermore say that one is a spectator, non-reactive, and the other guy is the conjugate of a weak and therefore engages in an equilibrium, and that's the one that's going to dictate what the pH of that solution is going to be. And so we were talking about that kind of stuff before, and we also noted that if you sometimes need the KB of a base, but you don't have it, you won't find it in your textbook, you can calculate it with the stuff that we said from the KA of something that you can find in your textbook. And we were doing some of that stuff, but you know, I thought that you should go through these problems and make sure you get the right answer, hide the approach, and then think about it, go back to it later, and start thinking about what they give you as far as a problem, what's in the solution, what's happening, what are the ions involved, which ones you can ignore, which ones you have to deal with their reaction, usually with water, and then use the ice table to connect what they're giving to what they want, which in this case, they want the pH. And sometimes in that ice table, like the one that's written here, we can fill this out. And as soon as you fill it out, you see that the X that you're going to solve for is not directly connected to the pH, but it's connected to the POH because it's the hydroxide concentration. So that's all right. You just have to remember another relationship that we looked at. And this relationship, remember, came out of one of the things that came out of the studying of the autoionization of water. And then the last time we were discussing, we left it off here at this plate. I wanted you to think about these two questions. And I added a few things that are not in your notes, that I looked at it and I said, well, this might make it a little more clearer, since later on we'll be hammering on this idea. So the questions are, to what extent does the reaction take place, and will the resulting salty water have a pH of 7 less than or greater than? So the first thing we noted was that we have an acid and a base, and I added up here, one of those guys are always in Chem 201, one of those guys are going to be strong. If they're both weak, we have a method to deal with the range of the pH, but we can't apply an ice table. It's too much of it's a complicated problem, and it's outside of the realm of 201. So in this case, here I have this generic HA, which is an acid, and I'm adding to that a metal hydroxide, which is a base. So which one of those is strong? Is it the acid or the base? Which one do you think in this case? I guess it could be either, right? I mean, it could be both. But it has to have at least one has to be strong. And so in this case, I'm saying that this one is definitely the strong because it's a metal hydroxide. And I'm going to assume that, well, I don't even have to assume that. It's a metal hydroxide and that it dissociates in water. And I see that I make water in a salt because it's a neutralization, Chem 200. You assumed correctly that this was a completion reaction. And you might be wondering why it is, and that's why I put to what extent does this reaction take place. And we're going to see, and we're going to argue that this type of reaction goes all the way. So there's no equilibrium here. When you have an acid and a base, one of them strong, there's a complete neutralization until you run out of one. But if there's a stoichiometric amount, then you run out of both. And what you end up with is salty water. Any questions on that, A? What I'm saying? I'm going to prove this hopefully in the next slide. Then B is, well, once you have that salty water, what's the pH? And last time I mentioned that it could be any of those possibilities. And it might seem odd to you that it is. But I think in a second or two, you'll see why. Okay. All right. So no questions. Let's see why. First of all, the extent of a reaction. So here I have two possible reactions, and I want to kind of gauge, where the equilibrium lies. So here I have what kind of a compound is HOAC. This is the acetate molecule. So this is like acetic acid. It is acetic acid. I just abbreviated acetate with an AC. Does anybody know what kind of a molecule acetic acid is? Well, it's an acid, right? What kind of an acid?
Weak acid
How do you know it's a weak acid?
from our lab last week.
Okay, that's good. Does anybody know why it's a weak acid from what we discussed previously?
It means it has a stronger bond.
It's even easier than that. It's not one of the 7 strong that you were supposed to memorize. Okay. So if it's not one of the 7 strong, then you are to assume that it's weak. Okay. Now, what kind of a base is this?
Strong base.
Yeah, correct. Strong hydroxide. Now, the question is there an equilibrium that sets up in this reaction where we have a strong base and a weak acid to form the conjugate base of the weak acid, that's the conjugate, and the conjugate acid of the strong base is water. So I want to try to figure out what the K is, what the magnitude of the K for this reaction is. And I notice that if I look at the reaction in reverse, it's just the weak base in water, then the K should be 1 over that KB. So I can look up this KB, and I won't find it, but I will find the Ka of acetic acid. So then I can calculate the KB using the Kw, and that comes out to something like that. Really small. So when I take that number and divide it into 1, I get a billion. So the equilibrium constant for that reaction is a billion. It's enormous, which tells me it's a completion reaction. There's no equilibrium. It lies way to the right towards the production of water and the conjugate base. Does everyone see that? Any questions on that? All right. Now let's take a look at the next reaction I have on this plate. I have the conjugate base. What kind of a base is this? This acetate anion.
Would it be strong?
Oh, it's weak. Now, why is it weak? How do I know it's weak? Because if I react this with water, then I know it forms an equilibrium with acetic acid. And that's weak. So when I have a conjugate that forms another weak, I know it's weak. If I have a conjugate that forms a strong, then I know that this is too weak to react. It's a spectator. So I can ignore something like that. It's a spectator. It's not going to react. I don't care what you put in there. But this guy, the acetate, that's going to form a little bit of weak. They're both weak. And so an equilibrium ensues, and I get a mixture of the two. That's what equilibrium is. It's not one way or the other. So I can deduce that this negative ion, which I surmise might be a base, is in fact a base in this case because it forms a weak acid when I react it with water. If it formed a strong acid, then I know it's not a base at all. It's a spectator. And it's not a strong base because it's not one of the strong bases that we looked at before. It's not a metal hydroxide. So you got to remember all the stuff that we talked about before, I think, to really appreciate what's going on here. So I think we pretty much pegged what this acetate anion is. It's a weak base. It's the weak conjugate base of acetic acid. So that's weak. All right, now I have it reacting with this guy. What is this? what can I consider H3O plus?
A weak acid?
Is it a weak acid?
Would it? mm,
Is it a weak acid like acetic acid or hydrofluoric acid or citric acid?
Well, it's not one of the
The seven.
strong acids.
Well, okay, good. I'm glad that you pointed that out because I'm going to argue that it is. Now take this HCl, right? We know that's a strong acid. And so what do we get with HCl? We get an arrow. And if I put, instead of representing this like that, if I include water in this reaction, say I put an H2 over there, then I could rewrite that H plus as H3O plus. And so you can say that H3O plus is also a result of any one of the 7 strong acids. So I guess what I'm trying to say is that H3O plus represents any one of those strong acids in water. That's the result of a strong acid. So I could replace that with HCl, HNO3, and so forth. Okay, so I'm going to label this also as a strong acid. It's a shorthand for, or not shorthand. It's an alternative representation of any of the strongs. And so now I got again, a base and an acid. I had an acid and the base previously, and I want to see to what extent this guy is going to react. So again, I have this reaction take place between a weak base and a strong acid, and I see what it forms. I have a weak acid and water. And I want to get a handle at what the equilibrium constant is, because I want to see to what extent this reaction takes place. And so I can look at the back reaction of that weak acid in water and say, well, I know the Ka for that weak acid, acetic acid in water. Then I can calculate the K for the forward reaction as the inverse of that. And I can look this up and see that it is weak. And I calculate an equilibrium constant that's very big, indicating that reaction lies way to the right. And again, I recognize that in both cases, there's a strong driving force for making water from an acid and a base when the acid or the base is strong. And it's also true when both are strong. As what I point out down here. Again, this is the result. H plus, I could rewrite that as H3O plus if I wanted, and then just put 2 waters over here. I could represent it that way. This is H plus is just the result of a strong acid. I don't care which one you pick. And then hydroxide is the result of a strong base. So I got a strong acid plus a strong base. I know that comes together and makes water. To what extent I can look at the K for that reaction as 1 over the K for the reverse, which is the autoionization of water. And I see again This reaction goes to completion. It has a humongous equilibrium constant, which tells me that that reaction lies way to the right. So in every case, there's a strong driving force for making water from an acid and a base, especially when one of those is strong. And if both of them are, it's even further to the right. So my argument here is you have to beware. Whenever you see a reaction involving a strong acid or base with a weak acid or base, the reaction is a Chem 200 type reaction. A limiting reagent type lies way to the right because there's a strong driving force for making water and a salty water. And you can look on the earth and see that a large part of the planet is made up of water. And it's not surprising because there's a strong driving force for making water. So that was kind of my point for these slides here. You know, number one, to what extent does it take place? To completion. And that's why I put an arrow like that. When one of these guys is strong, either the acid or the base. Any questions on A? Oops. All right, no questions. Now we get to the next question that I have back here. Will the resulting salty water of this completion reaction between a strong and a weak acid and base to form water and a salt, will that salty water have a pH of 7 greater or less than? So let's get to B. So this plate says, okay, many salts in water fully dissociate. So, all right, I make salty water and I know that that aqueous salt in water, AQ, and I know from my solubility rules that there's really no salt in there. It's really the ions of the salt. That's number one. Now I look at the charges of those ions and I say, well, those ions, they can be acids or bases. And when they react with water, I have to see whether they produce H plus or OH minus to prove it, whether they are in fact acids or bases. And so I look at what comes next. It says conjugate anions from weak acids are basic. Give me an example of a conjugate anion of any weak acid. Anybody know? Give me an example of a weak acid.
Acetic?
Acetic acid, yeah. Which we call HOAC in that previous slide. And sometimes you'll see that in lab. The formula is, that's the formula of acetic acid. So what is the conjugate anion of acetic acid? The acetate anion, right? This is a negative charge. So what this is saying here The conjugate anions from weak acids are basic. Well, geez, how could they be basic? Let me see. If they're in aqueous solution, then there's going to be lots of water around, so maybe it'll react with water. If it's a base, according to Bronsted, it has to accept that proton. And in the result, I get an increased concentration of hydroxide. So I would expect the pH to be what compared to 7?
Greater than.
Yeah, greater than. It's going to be basic. And so that's all this is saying. Does everyone understand that statement?
Yes.
All righty. Then you tell me what happens in the next one. Conjugate cations from weak bases are,
Acidic.
yeah. All right, now let's see if we can think about a example. Can you name a weak base for me? What is the stereotypical weak base?
CN-.
CN minus. Yeah, that is a weak base. Definitely. But I'm thinking of something else. The poster child for weak bases, the first one that we introduced the KB with was ammonia. Okay, that's a weak base. Let's look at the conjugate cation of this. What is the conjugate cation?
NH4 plus.
Yeah. Now, is that acidic? Let me see. I'll put it in water. Yeah, sure looks like it. I know this reaction is going to take place in an equilibrium because it produces a weak. So whenever you have a weak, it produces a weak and there's an equilibrium.
I actually had a question regarding this example. It was question 1 on the homework, and I thought that there were 2 examples of conjugate bases and acids, and yeah. So like, is the NH4 plus and NH3? Oh, is it because there's no minus? It doesn't count.
Yeah, let me see. Which of the following is a conjugate acid-base pair? Okay, so I got to think back to my definition of conjugate acid-base pairs. And I know they differ by 1 proton, right, in a
Yeah.
reaction. So that first example is not going to be an example of a conjugate acid-base pair because it doesn't differ by just 1 proton.
Mhm.
The same with the second. That differs by 2 protons. The third one, yes, that differs by 1 proton. H3O plus and OH minus, does that differ by 1 proton?
Oh, I guess not. I just always considered them each other's opposites, but
Yeah, it's a little more you got to stick with the definition a little more exactly.
okay.
Yeah, but I understand what you're saying. They're
Okay.
each other's opposites.
Okay, thanks.
Yeah, no problem. Okay. All right. So, any questions so far on this guy and this guy? All right, then we go down to the next one. Conjugate anions from strong acids are neutral. Now, what's a strong acid? Let's see, HCl. What's the conjugate anion that you get from that? Well, it differs by 1 proton. So what is it? What's the conjugate anion of HCl?
Cl minus.
Yeah,
mine.
good. And these guys are conjugates here, right? They're conjugate acid bases. Cl minus and HCl are conjugates. So now I have a conjugate anion of a strong acid, Cl minus. The solution is neutral. Remember, we talked about that. Why is it neutral? And not basic?
Is it because the Cl minus acts as a spectator?
Exactly. It's a spectator because it's the conjugate of a strong, and strongs don't form in water, they break up. All right. Any questions on that one? Okay, the last point, conjugate cations from strong bases are they're also neutral. Why? Because they're also spectators. So the idea is conjugates of strongs are neutral because of equilibrium. An example of this, a cation from a strong base, let's take our typical strong base, sodium hydroxide. We get Na plus OH minus. The conjugate cation is sodium. And we know that sodium is non-reactive. The equilibrium for this reaction lies way to the right. So again, it's a spectator. So conjugates of strongs are spectators and therefore result in solutions that are neutral. Doesn't change the pH of pure water, doesn't change the amount of hydroxide or hydronium in pure water because they're non-reactive. This guy just can't muster it up anything that's greater than is already in pure water because the equilibrium lies to the left. So it's neutral. Same thing with sodium. I don't know. Somebody could imagine that sodium could, I don't know, maybe make this and make the solution acidic. No way, Jose. Not going to happen. That's not going to push that equilibrium towards a strong base. Besides, we know from our solubility rules that this is completely soluble, sodium in anything. And so this is going to lie to the left, spectator. It's not going to change the pH from 7. It just doesn't add any. It doesn't add any more hydronium that's already in pure water. And then the last statement is just anions with ionizable protons are amphoteric, just to remind you that if you have multiple ionization possibilities, then it's possible that this could go to the right and form that equilibrium. Or not. Or it can add a proton and reformulate what it came from. So it's either an acid or a base. It's amphoteric. All right, so now we get into the nitty gritty. After those arguments, you know, we see that maybe there's a possibility for salty water to have a pH of 7 in the case when a strong acid plus a strong base is completely neutralized. So they're in stoichiometric amounts. And the only thing left is salty water. So it takes place to completion. We know that's going to happen. But the salty water contains spectators. So that salty water, as a result of a strong acid, strong base neutralization to completion, is 7. And we just argue here why. And I said, okay, well, maybe this is the base. If I consider it, you know, what's the KB for that? I argue that the KB equals KW over KA. I know the Ka of HCl, which is strong acid, is around 1,000,000. So this equilibrium constant is so small that this reaction doesn't take place. And like we said before, this is a spectator, and it doesn't change the pH of the water after a complete neutralization reaction. So that's one takeaway. Again, just to recap, when acids and base reacts takes place to completion and you get salty water, when that acid and base are both strong, the salts are both conjugates. The cation and the anion can be considered to be conjugates of strongs and therefore spectators, and do not change the pH. It stays 7. And that's what we alluded to back here. In these two statements. Conjugates of strongs result in neutral salty water. Any questions on that? All right. Moving right along, we go to our next possibility. And we're going to cover 4 of the possibilities of acid-base neutralization to completion. One we just covered, strong acid, strong base. The next one, number 2, is going to be a strong base with a weak acid. Number 3 is going to be a weak base with a strong acid. Number 4 is going to be the acid-base neutralization of a weak acid with a weak base. And we're going to take a look at all those possible resulting pHs. And like we said in that statement before, they're all possible, and it all depends on what's reacting and what's left over in the salty water. So you see where we're going with this? Anybody see where we're going with this? I mean, you're gonna have to go back and study it.
Yeah,
Okay, good. I never know if I'm making any sense at all. But I hope, even if it's just you're just kind of getting it, just a shadow of what's going on. I think you really have to go back and read through this and try to work through the logic on your own, don't you? It's not something,
definitely.
yeah, it's not something like history where you can read it and say, oh, that's a fact, this happened and go on. It's something that you need to process it through all the possibilities. And it's not simple. You got to use the logic to come to the appropriate and the correct solution. And this is what makes chemistry so hard and so challenging, I think, in science, because you ask these questions and the answer is, I don't know. It depends. It depends on what you're dealing with. And we're dealing with, I think, all the possible situations that can come up in a Chem 201 class. When I have an acid and a base that react and one of them strong, number one, I know it's going to take place to completion and I'm going to end up with salty water. Number two, that's pH of the salty water depends on what the identity of the salt is. What is in the cation? What is the anion? Can I identify them as acids or bases? Okay, so number two, this possibility. When I have a strong base, give me a typical strong base. Our strong base that we almost always use is sodium hydroxide. Why aren't you writing? Sorry about that. I must have hit something as usual. So there's our strong base and a weak acid. I'm just going to pick HF. And from our argument before, when I have a strong and a weak, it's not an equilibrium. It goes to completion to form salty water. So I get H2O plus NaF. But I know from my solubility rules that it's really Na plus aqueous plus F minus. There's my salt. Now, it says that resulting solution is basic. Can anybody explain why that would be basic?
The HF is not strong enough to cancel out the
Okay. Yeah, okay, look, it's a stoichiometric amount, right? So I can have 10 moles of this and 10 moles of that. And so they're all gone, right? I don't have any of that left. I have 10 moles of water produced, 10 moles of sodium produced, and 10 moles of F minus produced. Right, so that's what I have as a result, no equilibrium yet. And so I say, oh, I recognize that, Na plus, that's a spectator. So I can ignore it. Not gonna react, not gonna change the pH. What's this? I don't know. It's negative. Maybe it's a base. Let me see. I'll react it with water. Oh, I formed this HF. What's that? Oh, that's a weak acid. So I recognize HF as hydrofluoric acid. It's not 1 of 7 strong, it's weak. So that means this reaction will take place, will form an equilibrium, will produce a little bit of hydroxide. How much is enough? It's got to be greater than 1 times 10 to the minus 7. And then in that case, it will change the pH because this is a weak base. I know it's a weak base because it's the conjugate weak base of this weak acid. So I know that solution, that salty water, is going to be basic. And so that's what it says in this, on this slide. And it says, yeah, for example, the conjugate base of this weak acid is this guy. And if I react that in salty water, that's what I have left over from the neutralization that goes to completion. Between this weak acid and a strong base, I don't care what the base is, sodium hydroxide, calcium hydroxide, barium hydroxide, whatever, then I'm going to get a spectator cation, and this conjugate anion that's not a spectator because it's the conjugate of a weak, and it will engage in an equilibrium, just like we said F minus would up here. And so it will produce a little bit of hydroxide, and that's all we need. We just need a little bit. Whereas these spectators won't produce any, none. But these guys, when they're conjugates of weaks, they engage in an equilibrium, and that equilibrium is usually enough to change the pH. So again, it's not the conjugate of the strong that matters, it's the conjugate of the weak. And a conjugate of a weak acid is a weak base, so the solution's going to be basic. Okay. And so I I just calculated the Kb of this weak base from the Ka and the Kw, and it's not 10 to the minus 20 like it was with Cl minus, where that won't change the concentration significantly to change the pH. This guy is in the good range. It will change it. You know, if you have a 1 molar concentration, for example. All right, any questions on that? All right, then we move to the third example of a weak base and a strong acid. Remember, this was a strong base and a weak acid gives salty water. Now we have a weak base and a strong acid, again, that gives salty water. And we could ignore the conjugate base from the strong acid, but the conjugate acid from the weak base is going to lead this solution to be acidic. For example, this is the salt that remains when we neutralize a weak base with a strong acid. To completion, 100%. Strong driving force, for making salty water. And I leave out the aqueous. There's lots of water in these examples. And I recognize that in the salty water, I have a spectator, conjugate base of a strong acid, doesn't do anything, and a conjugate acid of a weak base. So this salty water is going to be acidic, just like It says up here. Any questions on that? All right, moving right along. The last possible situation is when we have a weak acid and a weak base. Remember before I said one of those guys has to be strong and it goes to completion. Well, when you have a weak acid and a weak base, then it doesn't have to go to completion. There's an equilibrium between the two, and the equilibrium problem becomes too complicated for Chem 201. But we can say that in general, if we look at the reacting weak acid and its Ka, and we compare that to the reacting weak base's Kb, we can predict the resulting pH. Whichever one of those has the higher value is stronger and will affect the solution more. And that will win the day, and it will dictate what the pH is. In other words, if I have a reaction between ammonium plus Cn minus, then I just need to look at the relative Kb of Cn minus compared to the Ka of NH4 plus, ammonium. I see this is bigger, so the resulting solution is going to be basic. In this case, it is. Okay. Any questions on that? Okay, now that's a lot to, yeah, go ahead.
I guess I'm a little bit confused because earlier, like in the homework, we were ranking the like Cn minus and Cl like to strongest and weakest.
Yeah, bases, correct.
And then we have like the rules saying that the conjugate cations from like a strong base would be neutral.
Uh-huh.
Oh, so is there a difference between like pH and then how strong it would be?
Yeah, the stronger the ion, the greater the change of the pH from 7.
Oh, okay. So if it was neutral, like if
Then
that,
there's spectators, like that first choice. They're both conjugates of strongs,
Mhm.
like that choice number 1.
Yeah. Okay. So being spectators, are spectators still, does that just apply like then when you see it in a reaction?
Yeah, so the spectators, as far as the pH is concerned, they're not going to change it because they don't react with water at all. What they'll do, I mean, we call them spectators because we're concerned with acid-base equilibrium now, but they're going to increase the ion concentration for sure. And they're gonna make that solution conduct a charge much better than if they weren't there. So our spectator terminology is just really applied to acid base equilibrium and pH. Those ions are still there and they can carry a charge, and I wouldn't want to be standing in a pool of sodium chloride when lightning hit because I would get electrocuted. But on the other hand, I could gargle with sodium chloride because I know the pH of salt water, sodium, when it's made up of the salt, sodium, and chloride, is going to be neutral. So I don't have to worry about getting burned.
Oh, okay. So they still maintain like their strength of,
Yeah, they still have their concentration.
okay. Okay. That makes
Yeah, they
sense.
don't disappear. They just don't have an effect on the pH.
Okay.
And that's why I'm calling them spectators. But if you wanted to look at conductivity, then hell no, they're going to make a difference,
Okay. Thank
whether
you.
they're there or not. Yeah, sure. All right, so I think we're almost done this chapter. The rest of the stuff here, like the next few plates, gives you one way to rank acid strengths. Actually, it gives you two ways to rank acid strengths because there's many. So in a question, you might be asked to rank this series of acids from weakest to strongest or something like that. So the first thing you should try to identify when asked to rank acid strengths is to see if you can be able to some way gauge the strength of the bond that needs to be broken. So say HX is an acid, right? And I know that I'm going to form X minus in water plus H plus when that bond breaks. So wouldn't it make sense that the weaker this bond, the easier it is to break, the stronger the acid is, because then it's going to create more H plus. It would make sense to think that way, I think, logically. So the first factor that you want to look at when given a series of acids and asked to rank their strength is look at the bond strength of the leaving H plus and see if some way you could rank that. Now, if that doesn't work, then see if there's some way you could rank the partial charge on that leaving hydrogen. That would be case 2. And if there's a way that you could rank that partial charge, then you could say that the higher that charge, the more acidic it is, because the closer it is to a full +1 in the dissociated H plus ion. So this is number 1 in ranking. If you can't do that, then you fall to criterion 2. And now there's many other ways to deduce or think about ranking relative acid strengths, but these are the two most common, and these are used as representative ways of thinking about ranking acids in Chem 201. If you get to organic, they might have other methods that you'll learn specifically geared towards organic molecules. Okay, so let's take a look at what we were talking about in those rankings 1 and 2. Now, here we have the question: rate or rank the relative acidity of this series of acids by just looking at them. Okay, so first of all, I notice that 3 are unlike 1, or 3 are like each other and 1 isn't. Which is it?
HF and then the other is,
Yeah. Okay, good. So now we want to use that criterion, that first criterion, and see if we can do a ranking on that. And so what I want to do is think about Chem 200 and think about trends in the periodic table. As you go down a column in the periodic table, what happens to the size of the atoms?
It's bigger.
Correct. And so I have HCl, HBr, and HI. And you know that the radius of a atom as you go down the column gets bigger. So can you tell me something about the bond lengths here? What's happening as I go down?
They're getting further apart.
Yeah, bond length increases. So what happens to bond strength?
It decreases.
Exactly. And what did we say about bond strength as far as acidity?
The weaker the bond strength, the more
Yeah,
acidic it is.
yep. There you go. So you have it. There's your ranking. And that's why. This guy's so small and short that it's strong, and it's not even the bond is strong, and therefore HF is not a strong acid. The bond length is too short and it's too strong to get rid of that H plus easily. Whereas the other guys are bigger, bigger, and bigger. And so we can go back now and take a look at the bond energies, and they fall in line with what we thought about bond strength and bond length. The shorter, the stronger. The longer, the weaker. And the weaker, the stronger the acid. It has the biggest Ka. So if there's any way that you can do that in any problem, somehow figure out that bond strength, then you could rank. And when I'm saying that bond strength, I'm talking about the bond strength of the leaving hydrogen in the acid. If you could rank that bond strength, then you could rank the strength of the acids. So if I wanted to fill in the line, as we go down the column of the periodic table, the atom size gets larger, so the bond strengths are weaker, and thus the bond strength gets smaller. HF would be the weakest acid because it has the strongest bond, and HI would be the strongest acid. You know, something like that. Any questions on that? All righty. The second one is that, say I have a series of acids and they all have the same bond for the leaving hydrogen. But I can look now at the electronegativity here, because that's the electron withdrawing power, and I see that it goes down. This guy has the greatest electronegativity, and then this Br, then I. So this hydrogen here would result at a partial charge that's greatest and closest to H plus. So this should be the strongest acid, and that should be the weakest. And I look at these charges and I see that's just what I thought. And I look at the Kas and it makes sense with my conclusion. Now, the other stuff, I mean, you could read this. The more oxygens you have, the more electron withdrawing power. So the higher the delta, the stronger the acid. And so that's in there. It shows some picture. This is a stronger electron withdrawing group than this guy. So I would say that this hydrogen delta is going to be greater than this one. So this acid should be stronger, and it is. So that's criterion 2. If you can't rank the strengths in a series, then maybe you can rank the partial charges based off of electron withdrawing groups down the chain. Okay, and so that's what that says. And that's the next one is just carboxylic acids, and it talks about this ring stability of the carboxyl group because you have this resonation back and forth. So essentially that negative charge is spread out over 3 atoms, and it's just more stable and allows this acetate or whatever this anion is to accept the negative charge better. And that's why carboxylic acids are acids at all, because they have this special structure. And that's pretty much the end of the chapter. Lewis acids we're going to get to a little more later on in the class. There's another definition of acids and base, and it centers around accepting a pair of electrons and donating a pair of electrons. So here's an example. You know, from the Lewis structure of nitrogen, it looks something like that. So it has this electron pair to donate, and that's going to be donated into an empty available orbital on the boron, because boron has empty orbitals. It doesn't have to obey the octet. This is kind of interesting when applied to metals. Metals have empty d orbitals. Water, you know, the Lewis structure of water has lone pairs of electrons, which are donated into the empty d orbitals, and they form these what's called coordinate covalent bonds. So metals don't exist all by themselves in water. They have this interaction with the water, these coordinate covalent bonds, these Lewis acid-base interactions. And in this case, with iron, it has a Ka that's greater than acetic acid. So you can get more H plus from an iron cation than you could from acetic acid. And we have more on this in a later chapter at the end of the course that we're going to come back to this and look at. But I just introduce it here just because it goes along with the end of that chapter and including a more well-rounded look at possible acids and bases. But we'll get back to that. That's just an add-on. All righty, guys. I'd like to ask you if there's any questions on anything. I know we went over a little bit this time, so I'm just going to hang out. I know one person has some questions about the lab online activity 2. So I'm going to answer some questions about that lab, hopefully. If you want to stick around, fine. If you have other questions, you can stick around as well.
Thank you.
Thank you, guys.
Thanks, Phil.
Thank you.
Thank you.
Yep.